This video is about the unsaturated flow of water in soils. But in order to introduce this, it might be worthwhile to review saturated flow in soils one more time. When we talk about saturated flow in soils, what we really mean is that the soils are completely saturated with water, meaning all pore space is filled with water. And flow through the system can then happen through all the connected water-filled pathways, in which small and large pores contribute to the flow of water. We further learned that the Darcy law can describe this flow. We learned that the amount of water going through a cross-sectional area of soil in a given time is proportional to the driving gradient. And we also learned that the flow regime can be described by the saturated hydraulic conductivity, which was something that described both the pore structure, the size, the connectivity, and the tortuosity of the pores, as well as the properties of the fluid, such as viscosity and density of the fluid. Now let's contrast that with unsaturated flow. By unsaturated, we mean we now have a three-phase flow problem. We have water, air, and solids, and the air-filled pores will not be contributing to the flow of water, but it is only the connected water-filled pathways that continue to do that. And what we also learned in the past is that as we start to desaturate a soil, it is the large pores that start to desaturate, meaning that under unsaturated flow, it is only the small pores contributing. If only the small pores are contributing, that also means that the size of individual flow paths has decreased under unsaturated flow conditions. And if you remember back to the Hagen-Poiseuille law, which stated that the flow was proportional to the radius to the fourth power, you must realize that now the flow has decreased substantially, and substantially being by the fourth power of the radius, because of the introduction of air and the decrease of water-filled pathway sizes in this flow regime. The other thing that happened is that the flow path has become longer and more tortuous. And it is because of these two effects that the hydraulic conductivity, K, must be much smaller than the saturated hydraulic conductivity. So the hydraulic conductivity has to decrease as we decrease the water content in the soil, as we start to desaturate the soil. We may relate this back to the water retention characteristic that we've spent so much time talking about. Remember, in this characteristic, we linked the volumetric water content with the matrix potential of the soil. It had this characteristic S shape. And now we want to look at how the hydraulic conductivity decreases as we decrease the water content. We know that the hydraulic conductivity has to be at its highest when the soil is saturated. And that the hydraulic conductivity would decrease as we go to lower water contents. We might also remember from our water retention characteristic that there is a residual water content, water that is simply held in thin films around particles. And at this point, the water films are no longer connected with each other, and the hydraulic conductivity would have to drop to zero at this water content. Now, the decrease in hydraulic conductivity is not linear because of the Hagen-Poiseuille law and the fourth power of the radius describing the reduction in flow, as well as the increase in tortuosity. So the decrease in hydraulic conductivity most likely will follow a relationship such as this one. So to summarize, under saturated flow conditions, we can use Darcy's law to calculate the flux as the product of a scalar saturated hydraulic conductivity in a driving gradient delta H over L. The H, or the potential in Darcy's law here, will be the sum total of pressure potential, gravity potential, and solute potentials driving the flow of water. When we go to unsaturated soils, we change Darcy's law in two major ways. The first one being that the driving gradient now includes the matrix potential, and the pressure potential here being zero because we are at unsaturated conditions. And the other change is that the hydraulic conductivity now becomes a function of matrix potential or water content, where the hydraulic conductivity decreases with water content and decreases also with matrix potentials becoming more negative. So now let's see how the hydraulic conductivity changes as we go to lower water contents or more negative matrix potentials. We'll start out with the sand. The maximum value of hydraulic conductivity that we see at saturated conditions corresponds to the saturated hydraulic conductivity. And as we go to drier conditions, the hydraulic conductivity decreases. Now contrast that with the loam soil, you'll see that the saturated value for the loam soil is lower than that of the sand, which is consistent with what we've learned in the past. And also that under wet conditions, the hydraulic conductivity of sand is greater than that of the loam. However, as we go to dry conditions, the situation reverses, and now the hydraulic conductivity of the loam is greater than that of the sand. To explore why that is, it might be useful to remember the water retention curve. The sandy soil, made up of large particles, has large pores in between them, and the pores don't tend to be very tortuous. So under saturated conditions, when all of these pores are water-filled, that means we get a high flux for a given driving gradient through the sandy soil, and that is reflected in the higher saturated hydraulic conductivity and in the higher hydraulic conductivity under wet conditions for the sand compared to the loam. However, as we decrease the water content in the sand, we quickly empty out those large pores, and we're left over only with a small number of pores that are of small radius, and the water flow pathways become more tortuous quickly in the sand, which means that the hydraulic conductivity decreases relatively rapidly in the sand. We contrast that to the loam, which has smaller particles, a range of particle sizes. It will have small pores that are water-filled under saturated conditions with a higher tortuosity compared to the sand at wet conditions, which is reflected in the lower saturated hydraulic conductivity. But because of its larger pore size distribution, as we start to decrease the water content in the loam soil, we remain enough water-filled pores to still be able to transmit water through this pore system compared to the sand, which at the same water content or matrix potential would have already desaturated most of its water transmitting pores. And that is why under dry conditions or negative matrix potentials, we see that loam soil can actually transmit water faster than a dry soil for the same driving gradient.